Thank you again. And first of all, I would like to thank the organizers for organizing this workshop. Today, I will give you a quick overview of the RISC-V in space activities that we are doing in collaboration with several partners, in particular Thales Alenia Space Italy, E4 Computing Engineering, Politecnico of Torino, Politecnico of Milano, and University of Bologna, in the context of the European funded project, which is named ISOLDE. ISOLDE is a CHIPS JU funded project. It lasts for 3 years, and now we are reaching the end of the second year. It involves about 40 different partners, which involves large industries, small, medium enterprises, academic and research institutions coming from 9 different European countries. And the goal of this project, as well as other several projects along the same lines, is the one of enhancing the European RISC-V ecosystem, in this case specific for high-performance system on chips at the edge, in such a way to improve the ecosystem, the European ecosystem that is already present, to reach a level which is compete or be even better than what is already existing with commercial or proprietary alternatives. The activities done in the context of these projects are several, starting from the development and the design of RISC-V architectures, cores, accelerators, software and software stack, providing a list of IPs based on RISC-V, most of which will be released as open source, with the final goal to provide a robust ecosystem and a robust compute infrastructure based on RISC-V that will later be demonstrated in the context of this project on several use cases coming from industry, such as, for example, aerospace, automotive, smart home, etc., etc. We, as Leonardo, are coordinating one of these demonstrators, which we named Space Demonstrator. In this Space Demonstrator, we will try to validate and harness the capability of RISC-V processors, accelerators, and software stack for bringing high-performance processing capabilities closer to the source of data on satellites, so directly on board. This is also important because we want to minimize the uplink and downlink requirements, so transfer less data to ground, transfer only the information, the relevant information to ground, and bringing an AI model and machine learning models closer to the edge, we can also enable real-time decision-making and automatic coordination among the satellites. Clearly, in order to do this, we have to work very closely among the application developers, which is, let's say, us, as Leonardo, and Thales Alenia Space Italy, the hardware developers, and the software stack developers. As I will mention more in detail later, we will be focusing for this space demonstrator on 2 AI and machine learning applications. One, which we call hotspot detection, so an AI model that runs using multispectral data for doing hotspot classification based on raw images, and one is a machine learning model which will be used for satellite health monitoring. What we will do in the context of this project is, once the design of the architecture has been done and it has been implemented on FPGA system, we will try to evaluate the capabilities and the performance of these AI machine learning algorithms to see if what we design could be viable for being brought to space. Now, a couple of words about hardware architecture that we are using in this project. As I was mentioning, Leonardo is for sure not a company which designs chips. We are a company that sells services and develops final applications. So we are end users in this chain of the RISC-V ecosystem. However, it is important to start from the application that will have to be run on space, because this provides a list of requirements that we can provide, we can discuss together with our collaborators, and with this kind of discussion, our collaborators can provide us a reasonable, good design platform for which could suit best our applications. So doing this kind of discussions with our collaborators, the proposal that they came up with for the architecture is to start by host platform, which is based on the Cheshire system, which is Linux capable, and consists of a single CA6 core 64-bit. Then there is an access crossbar that connects this core to all the relevant peripherals. And what is important for us is that we also have a bunch of accelerators dedicated to accelerate typical workloads from AI and machine learning applications, so matrix multiplication, matrix vector, and vector-vector. Accelerators could be something like tensor process unit, parallel computing unit, and so on and so forth. So the general idea of this architecture is that there is a host system with CA6 core that executes the operating systems, configures and coordinates the accelerators, controls the peripherals, etc., while the accelerators are mostly dedicated to offload and accelerate the compute intensive tasks coming from AI and machine learning applications. Of course, all this can work properly only if we have a relevant software stack that enables a developer to make full use of the hardware that has been designed, and in particular of the new accelerators. Here the idea, the desiderata, is that the impact on the developer of the application is very little, if not zero, in the sense that ideally we would like AI or machine learning application developer to train its own algorithm on an HPC center on ground, starting already collected data, and automatically or semi-automatically be able to use the software tools coming from the RISC-V ecosystem to bring an optimized, quantized, prune, efficient model on the edge with little effort. Of course, this requires a lot of work from the partners working on the software stack. And here we have a couple of examples of libraries and compilers that are partially being developed in the context of this project. Now, coming back to the applications. As I was mentioning, we are working on two applications. One is a purely AI model for hotspot detection. So here the idea is to have a model which, at the edge, acts on the raw images collected from multispectral sensors and automatically determines if there are hotspots such as volcano or wildfire events. We started from training the algorithm from a public dataset, TROS, with data from Sentinel-2 missions. And the only issue here is that the dataset was not labeled, so we had to label it by hand. And this took some time. Another thing I should mention is that the raw images in this dataset cannot be used as they are. They need a slight preprocessing step, as a light co-registration that also needs to be performed on board. As far as this architecture is concerned, we are working mostly with the 3D convolutional blocks, and this is simply because multispectral images have information from 2Ds, which are the usual 2D dimension of the images, plus all the information coming from the fact of being multispectral. So these 3D convolutional blocks should give a more comprehensive representation of the information collected in this data. The second application, the satellite health monitoring, is instead a first attempt to automatize fault detection methodologies that are usually very time requiring from a user point of view. So we would like to see if machine learning methodologies could speed up this process of detecting early anomalies and reduce response times for potential faults. And in this case, we are working with a dataset that consists of time series containing telemetry data. The model in this case is a convolutional autoencoder, which also includes LSTM layers, which are the typical layers used for analyzing time series. The dataset that we are using comes from a real-world dataset, although we are introducing some simulated anomalies because, as you can imagine, anomalies are very, very rare in real-life situations. And also in this case, we have to do a light preprocessing steps, simple things such as data conversion, data normalization, that also needs to be performed on board, but is also part of the full workflow. So just to summarize, in the context of the ISOLDE project, we are coordinating the space demonstrator with the goal of validating the possibility of using the RISC-V ecosystem to bring AI machine learning models on space, keeping high performance computing processor while at the same time keeping the energy consumption low, with all the constraints coming from being in the space environment. We are working on 2 applications, AI and machine learning. Currently, we are at the 2nd year of the project, so we are in the phase of implementing the system on chip and the first accelerator on the FPGA. After this first phase will be done, we will start by evaluating the algorithms there, and I hope that by the end of the project next year, at the next conference, I will be able to give you more details on the results that we obtain. So, thank you very much.